Hi, folks. Welcome to the Neo4j Twitch channel. My name is Will, and we will be working with GraphQL and GRANDstack today, every Thursday at 2 p.m. Pacific. So last time we were working on building a real estate search app with GRANDstack, kind of like a Zillow clone. And we're going to pick that up today. Last time we sort of got everything started from the GrandStack starter project, and then we deployed to Netlify, and we started looking at some data modeling using the arrows diagramming tool. So I pushed up everything to GitHub. I'll drop this link in the chat here. There we go. So if you want to follow along, this is the GitHub project. And last time we just used the GrandStack starter project to create our sort of skeleton starter with the GraphQL API, React application on top of Neo4j. Last time we used a Neo4j sandbox instance to do this. Here's sort of just a kind of a rough sketch of what we're building. So the front end, this is a React application. We use Apollo client to make data fetching queries to a GraphQL API. Our GraphQL API is a Node.js GraphQL server that's built with Neo4j GraphQL JS and uses the Neo4j JavaScript driver to send queries to Neo4j. Previously, we had this in Neo4j Sandbox, and then queries come back, data comes back through the GraphQL API and to our front end. So that's the basic architecture. This is the data model that we had sort of sketched out last time, just kind of the initial nodes and relationships there. And I talked a little bit about how data modeling is often driven by the requirements of our application. So I think of this as this iterative process that we go through where we start defining the requirements of our application, and then we identify what are the entities, those are the nodes, how are they connected, those are relationships. And as we start to draw out our data model, we start to look at the questions that we want to ask of the data. So as a user, I want to search for properties for sale in a specific city so that I can view property details. And I want to at least think of some traversal through the graph. If I can write the cipher query for it, that's great. So that I know that, yes, this data model addresses the requirements of my application, right? So let's take a look at an example of what we want to build here. So this is Zillow. It's a real estate search application. We want to look for properties for sale, in this case in San Mateo. Right, and so I can search by city and view property listings. I can view detailed information about a property, such as its square footage, the number of bedrooms, and so on. All right, so that's the basic idea for this requirement. So what I want to do in today's session is pick up where we left off with our graph data modeling. I want to see sort of that we've addressed some of our use cases with this data model. Maybe we need to tweak this a little bit. And then I'd like to get started with importing some data into Neo4j, and then see if we can start querying it with GraphQL. So first, a little bit about data modeling. So we were using this tool called Arrows, which is this graph data modeling, graph diagramming tool. It's hosted on the web. It's very simple. It uses local storage to store our model, which we can then export in various ways. Let me drop a link to that in the chat. Cool. So one thing that I really like about arrows is that we can check in this markup that defines our data model into version control. So here I've pushed the markup for my data model up to GitHub. So I can just copy this out of the README. And then if I go in arrows to export markup and paste in what I copied out from the README, that will load my data model, and then I can go in and start tweaking things. Cool. So in this case, let's look at what requirements we've identified so far. Let's clean this up a little bit. So we said we have listings. Listings were created at a certain time. So in Neo4j, we have a date time object that we can use. Then we have this Boolean flag, is this listing active? And we'll probably have other information on our listing, maybe such as like asking price, which is going to be an integer. So this is a listing of a property, and maybe this property is in a specific city. Let's reverse the direction of that. Okay, and then our property has a address, it has a location, and then it has bounds. So location is a single point. So in this case, latitude and longitude. And then also it has this bounds, which is property, which is an array of points. And this is what's going to be defining the geometry, essentially a polygon of latitude and longitude points that are going to define the boundaries of the property parcel. And why do we have both of these? Well, we have one latitude and longitude to represent if we just want to annotate a map and show the point on a map. Close down Zillow. Let's take a look here. So San Mateo. Let's choose this one. Right, so we can see that, okay, it's annotated on the map as a single point. But if I maybe view the details of the property, and if I view the map for the details of the property, now I have the ability to view the lot lines, and the lot lines are going to show me how big in the dimensions of the actual lot for the property. So we keep track of not only a single latitude and longitude point to represent the property so that I can annotate it on the map, and so that I can use that in maybe search on the map, something like that. But then also the bounds, because I actually want to do work with that polygon geometry. Okay, so that's what I have so far. Let's look at some of the requirements that we have here. So the second one we identified is, as a user, I want to limit my search to properties with certain attributes or range of attributes so that I can narrow the results to those relevant for me. Okay, so what does that mean? Well, if I look at this example in Zillow, let's close out of the property details. I have, let's say, like a bed and bath filter. So maybe I want at least 2 bedrooms, or let's say at least 4 bedrooms and at least 2 bathrooms. Right, and now this is changing my search results. And there's a lot more I can filter by things like home type, by things like price range, and so on. So let's take a look at our graph model. Now, last time when we were talking about this, I made the distinction between a listing and a property. And the reason for that is because listing is sort of at a point in time. I may have a listing of a property, maybe it sells, and then 2 years later, the people who bought that property, then they list it and sell it. And so it's really a listing of the same property. So I can have multiple listings per property. And then the question is, okay, well, I have lots of detailed information about the property and the listing, things like number of bedrooms, square footage, and so on. And the question is, okay, does that belong on the listing or does that belong on the property? Here we've started to add it to the listing. So here we have number of bedrooms as a property on the listing. And this is a good question. This is sort of getting at this idea of entity versus state, right? So the property is kind of the entity, and maybe when it's listed once, it has 2 bedrooms, but then someone bought it and did a remodel, and this time it has 3 bedrooms. Or perhaps I know there can be some discrepancies in how things like square footage are calculated. So maybe the next time that it's listed as maybe slightly different square footage and so on. So the way I like to think of this is the property that represents the entity, and the things that are never going to change should be properties of the entity, in this case, the property node. So things like address, things like the location, latitude and longitude, those are not going to change, but the detailed information of the listing, that may change based on sort of changes through time. So that is sort of the state of the entity. So anyway, that's how I like to think of that. But our question was, can we sort of envision a graph traversal where we are searching now for properties in San Mateo that have at least 2 bedrooms and 4 bathrooms, or 4 bedrooms, 2 bathrooms, whatever. So yeah, if I have bedrooms, I can also add things like bathrooms and so on. I can add things like square footage and so on. So now when I'm searching, I just have a predicate that is going to specify the number of bedrooms is at least 4, bathrooms at least 2, and so on. Okay, so this requirement, I think, is addressed by our data model. And then the next requirement that we identified last time is, as a user searching for properties, I want to view property details so I can learn more about the listing. Yeah, and again, I think that's addressed in our data model, since we have the property details information in the listing. We can think of things we might want to add here, and when we get to adding the functionality of creating a listing for a property, we'll see maybe how to address some of the specifics. But sure, we can see that we just sort of need to return the properties of this node to be able to show the user some detailed information about the property. Cool. Oops, there we go. Okay, so that's sort of addressing the requirements with our data model. Let me check the chat here just to make sure I'm not missing any questions. Again, feel free to reach out in the chat if you have any questions or thoughts. Okay, so that I think is a good initial discussion of graph data modeling. Again, this is an iterative process. As we discover more requirements, we may need to update our data model, and that may then inform some of the different queries that we run. So the next thing I want to explore today is starting to import some data into Neo4j and start to sort of see how we can use GraphQL to start to query Neo4j. And I thought it would be interesting to start to look at how we can start to import this property and the city node as well. So if we jump back to our example in Zillow here, where we're searching in San Mateo, and remember, if we zoom in really far, we can see that, well, we have lots of information about all of these properties within San Mateo. Both, we know, even if they're not for sale, the bounds of the property, we know the square footage. We can see kind of a Google Street View. We have an estimate of how much the house is worth. We have things like property taxes and so on. And this data in the US anyway is, for the most part, public data, information on parcels and property taxes and size of the house and so on. This is typically public information that is available at the state or county level in the US. I'm not sure how this works in Europe. But anyway, I thought it would be interesting to start to import some of this data into Neo4j and see how we can build a GraphQL API on top of that. So I found for the state of Montana some of this data. So I was working on an unrelated project and came across that. So we'll start here importing some data, some parcel data from the state of Montana. This is their FTP server, which I'll post a link to in the README, and also add all the steps we go through to import this. So what we want to do, let's pick, let's start with Gallatin County, and we can see we have sort of an XML file that tells us what the data looks like. And then we have a few different versions of this data we can download. One is a GDB file, which I think is some sort of geospatial database format. That one I'm not too familiar with. But the other two formats are shape files. So I'm going to copy the link address for this one. And let's jump into a terminal. So this is a bit bigger. This is, there we go, make that a bit readable. So here I am in the Willow GRANDstack directory. Let's create a data directory. And let's pull down this zip file. Import. For some reason that didn't work. Can you not wget a zip file? That's fine. Let's do a save as. Okay, let's save this to we want have it in, I think I have it in my home folder. Just sitting there, Willow GRANDstack in data. Okay, cool. So let's unzip that. Okay, and so we have some shape files now that has parcel information for Gallatin County, Montana. What we want to do now is load this data into Neo4j. How do we do that? Well, if we take a look at at this shapefile, we can see that this is a binary format. So there is a plugin that allows us to load shapefiles into Neo4j. There's a spatial extension. But what I'm going to do today is convert this shapefile into GeoJSON. So GeoJSON is just JSON for a specific schema. So it has specific structure for storing things like geometries and metadata about those geometries. And GeoJSON is nice because once we have that, it's first of all, it's basically human readable. We can look at a JSON file and sort of understand what data is there. But then also there's a whole suite of tooling that we can use for importing JSON into Neo4j, for transforming it, and so on. So I'm going to use a tool that's part of GDAL. Let's take a look at that. Let's close that notification. I'll drop this link in the chat too. So GDAL is part of this suite of command line geospatial tools. This specifically is useful for transforming geospatial data files into different formats. I installed this. This is a Python command line tool. I think I installed this through Anaconda. But there's different ways to install these tools. Specifically, the tool we want to use is OGR to OGR. So this is a command line tool that is going to allow us to convert from the binary shape files that we downloaded into GeoJSON. So let's go ahead and do that. So what I want to do is OGR to OGR. I want to generate this file called gallatin.geojson. This -f, this is just saying what format do I want to output, right? So I could go from GeoJSON to a shapefile, or lots of other different formats. But in this case, I want to output GeoJSON. This LCO, so this is an option that's going to allow me to specify what is the ID field in the GeoJSON. And in this case, I just happen to know that we have a field parcel ID for each parcel, and we want to treat that as the ID field in our GeoJSON. Okay, this next option, let's look at the docs for this, is T_SRS. So this is saying, okay, which transformation do you want to use? Which coordinate reference system do you want to use? And I forget which the shapefile is using, but we want to specifically use WGES84 projection, also known as the EPSG 4236 projection. This is, I think, commonly called the geographic reference. So that's what we want to use there. And then the file we want to pull in is the shapefile that we just downloaded. So let's run this, and this will take a minute or so. If you hear a bit of background noise, my neighbors are getting some trees cut down, so apologize for that. That's just some chainsaw noise in the background. Okay, so now we should have a gallatin.geojson shapefile, or sorry, GeoJSON file. So here we're just looking at the first few lines of it. So here's just sort of some metadata. Now we have an array with the key features. And then for each one of these features, we can see that we have, first of all, telling us the type feature. Okay, great. We have an ID. This is where we specified parcel ID from the shapefile up here. And then we have an object properties for each one of these features. And within properties, we have things like the GIS acres. So I guess that's the acreage for this parcel that we're looking at. We have some information about property taxes in this case. So for the 2020 tax year, we have the assessment code. We have things like the address, how big is it, and so on. I think for some of these, we even have information about number of bedrooms and so on, things like that. Cool, and then we have a geometry property. Let's take a look at that. So here's our geometry. This is of type polygon, and here are the coordinates. So this is a list of latitude and longitude pairs. So this is what forms the polygon of the parcel. Cool. So how are we doing on time here? Okay. Oh yeah, plenty of time. Great. Okay. So we have this GeoJSON file. Now we want to start importing this into Neo4j. So let's see how we do that. Last time we were using Neo4j Sandbox. That's just a really easy way to get started and have a hosted instance of Neo4j running in the cloud. This time I'm going to use Neo4j Desktop. Neo4j Desktop allows us to run Neo4j instances locally. Think of it as sort of a delivery mechanism for Neo4j database. If you haven't used Neo4j Desktop before, you can get it at neo4j.com/download. Drop that link in the chat. And just close some of these windows here. Okay, so let's create a new project in Desktop. And let's call it Willow GRANDstack. And we'll create a new database. I want to create a local database. I'm going to choose version 3.5.18. The reason I'm choosing this version instead of one of the newer 4.0 instances is because there's a specific plugin that I want to use later on that I know works with this version. Not sure about the 4.0 version. We give it a name and then a password. Can be anything. We just have to remember what that password is later on. Okay, so we have some JSON data. How do we import that into Neo4j? Well, there is a There's a library for Neo4j called APOC, which stands for Awesome Procedures on Cypher. And APOC you can think of as kind of like the standard library for Neo4j. It has a ton of tools for things like data import and export, things for formatting data, things for virtual nodes, things like that. It exposes more complex path expansions and so on. So specifically, we're interested in the data import functionality in APOC. And we can see here that we have a load JSON procedure. So Cypher itself, you may have used load CSV, which is built into Cypher. So we can stream CSV files directly into Neo4j, and with Cypher, specify how we want to create that data in the graph. And APOC load JSON gives us similar functionality, but with JSON files. Cool, so I'm going to go in here to manage plugins and install APOC. So that will install the APOC library into this Willow GRANDstack database that I just created in desktop. And then because I want to load a file locally, I want APOC to be able to access files in my file system. I need to add APOC dot import dot file enabled equals true, I think it is. APOC dot import dot file enabled true. Yep. So in order for APOC to be able to access files on the file system to import, I need to add that in my Neo4j settings. Cool, got that. So let's hit apply to save that. And then we'll go ahead and start Neo4j. Okay, there's one more thing while this is starting. There's one more thing we need to do. If we look at the geometries, we can see that we have polygon geometries, but let's do a grep for multi-polygon. And we can see that we also have lots of multi-polygon. Oh, this is a long one. Okay, multi-polygon. So the difference between polygon and multi-polygon is polygon is sort of one single set of coordinates that define a polygon, but a multi-polygon can have polygons maybe within the polygon. So maybe this is the boundary of a parcel, but there's a piece that's cut out, or there are two disjoint polygons. And what I want to do is filter out any of the parcels that have multi-polygon, because the way I want to deal with polygons as a list of points is a bit too simplistic for handling multi-polygons initially. But actually, I think maybe we may not even get to working with polygon geometries today. So we'll save that for next time. So in that case, I'm ready to grab this GeoJSON file. So let's go here into desktop. Let's open a terminal. So one thing that's nice about desktop is I can open a terminal, and because desktop manages a bunch of different installations of Neo4j database, it gives me the ability to open a terminal with all of the binaries loaded into the path. So I can do things like Cypher shell or Neo4j admin, and I can run and they're on the path specific to this installation of this Neo4j DBMS that I want to work with, which is nice. And you can see if we look at where this is buried somewhere within within the Neo4j desktop installation, but I don't need to worry about that. So if we look, we can see we have some few directories set up for us. There's a data directory. That's where the actual data store for Neo4j data is written. There's a conf directory. That's where my settings are written. There's logs and so on. What I want is to go into the import directory. By default, this is where files will be read from for things like APOC load JSON, load CSV, and so on. And what I want to do is copy, not from that, I want it from Willow GRANDstack, data, Gallatin GeoJSON. So I want to copy the gallatin.geojson file that we created now into this import directory so that I can reference it with APOC load JSON. Okay, cool. So let's fire up our Neo4j instance is running. Let's go ahead and open it with Neo4j browser. So it opens over here. Oops. And there we go. Cool. So this is a fresh installation of Neo4j. There's nothing here. I can verify that. Do match in, return count in. Nothing here. But let's import some of our property data. So APOC load JSON. And it is gallatin.geojson. And so by default, this root path is going to refer to within that import directory for this installation, which is why we moved that file over. And then we want to yield value. But remember the structure of this GeoJSON file. Let's go back and look at that. Head Gallatin was such that all of the data that we care about is jammed under this features key. So I don't want to just return sort of this whole JSON file. That's going to be, I don't know, however many hundreds of thousands of rows. Instead, just to take a look at this, let's do an unwind over value dot features as feet and return the first 10. So how does this APOC load JSON work? Well, it parses this JSON file and then yields an object. This is like a map, like a dictionary, which I can then work with in Cypher to specify how I want to create that data in Neo4j. So here we're saying for the features array, so for this giant array of features, I want to iterate through that, and I want to alias now each one of these objects, each one of these dictionaries or maps, I'll use those interchangeably for our purposes. And then let's just return the first 10. So let's see if this works. So this is parsing our JSON file, and then it's going to iterate over that features array and hopefully should return just the first 10 for us. Cool, and so here's the first one. So it returns back this this object that has a geometry key with polygon as the type and a bunch of coordinates. And then we have parcel ID, and then we have a bunch of property information. Cool, so this is the information we have for one parcel, one property. One thing that's nice about load JSON with APOC versus load CSV with Cypher, if you've used load CSV before, you may have noticed that by default, there's no sort of interpolation of the type of our data that we're reading in. So everything is by default treated as a string, and we kind of need to cast that specifically. But if we notice here, we've interpreted the type of the objects here. So property ID, this is an integer, this is a string, total value, this is an integer, shape length is a float, and so on. So that's one nice thing we get with APOC load JSON. Okay, well that's fine. We need to do more than just sort of look at these in Neo4j in the browser. Let's actually create some data. So this is just parsing that JSON file and then just returning it to the browser. We haven't actually created any data in the database yet. So let's now do a for each. So again, we want to iterate over all of our features. So we'll say for each feat in value.features. And by the way, I like to use the Cypher ref card. If you haven't seen this, drop a note link to that in the chat. Cypher ref card is just sort of quick reference documentation for lots of the common Cypher functionality. So let's search for each. So for each allows us to, as it says, execute a mutating operation. That's for each relationship in a path. For each element in a list is what we want to do. So this is the syntax for each, the alias that you want to use in whatever list, and then a pipe, and then whatever your mutating operation is going to be. So in our case, we want to execute a create operation, creating a property node for each element in that features array. Cool. So what is that going to look like? Well, something like create property. So this will create the node, and then we want to set some values. Well, if we look back, I closed the tab. Let's run this Cypher query again to show us the first 10. Well, let's just look at the file here. So for each feature, we have an ID, and then we have a properties object, which goes through here, and then our geometry object is separate from that. So let's go ahead and set, oops. Unwind. Oops, I must have cleared out what we had so far. That's fine. So we said it was for each feat in value dot features, and then a pipe, and then create p colon property, and then in curly braces, let's set ID to feat ID. And then because we have this, this map of key value pair objects anyway, we can just say set p plus equals feet.properties. And what this will do is take this properties object and just add these as key value pair properties on this node that we just created. Cool, so let's run this and see what happens. So this should be iterating over all of these features in our GeoJSON file, creating a node for each one, setting the ID property, and then setting all of the key value pairs in the properties object as properties on the node. Let's check the chat, see if we have any questions. Doesn't look like it. Okay, so once this is done, then the next step is to see how we can expose some of this data through our GraphQL API, and then sort of see how we can maybe do some sort of filtering and so on. Okay, so this created, what did that say, 50,000 nodes. Okay, so let's match property. Let's look at the first 10 of these. Okay, so here's one. We can see some information about this, such as the type of property, the total acres, what city it's in, and so on. Cool. Okay, so there is obviously not all of the data that we need, and we need to flesh out our data model a bit more. If we look at our data model in arrows, there are some things in here that we might be able to extract. We might be able to maybe pull out the city, pull out some of bedroom, bathroom square footage, and so on. But what I want to do in the next few minutes is see, okay, now that we actually have some data in Neo4j, how do we then start to change our GraphQL schema and expose a GraphQL API and start to query this data in Neo4j. So let's see if we can do that. And again, let's run a call db.schema.visualization. All right, so far all we have is property nodes, so not very graphy at this point, but that's okay. Let's just make sure we can query some of this data using GraphQL. Okay, so this is now back in our Willow GRANDstack project. This is exactly the code that's up on GitHub. And if I do an npm run start, this will start both the GraphQL server, and remember we also had this skeleton React application. So the starter project that we started from had data for a sort of business reviews application, and what we wanted to do now is sort of start to change that to reflect our real estate search application. So let's jump over. It says our GraphQL API is running at localhost 4001/GraphQL. So this will give us GraphQL Playground, which we can use to query our GraphQL API. And if we take a look at the docs, yep, we can see our schema has things like users and businesses and so on. So let's change that, and instead let's set this up so that we're able to query data based on our property node that we have in Neo4j. So we want to change our GraphQL schema to reflect that. The first thing that we want to do. And we'll notice we have some errors here saying that we're unable to connect to Neo4j. And yep, that is reasonable. Last time we were using a Neo4j sandbox instance. So if we look in the /api.env file, we have the connection credentials to our Neo4j sandbox instance, which I think I have since terminated and moved on to other things in sandbox. So let's change this now. Let's change our Neo4j URI connection string to point to localhost colon 7687. That is the default for local databases that we created and started using Neo4j desktop. So this is going to refer to that database that I have running in desktop. The username, we left that as Neo4j, and then the password I set as let me in. Okay, and then if we look in API source schema.graphql, so these are GraphQL type definitions. This is what's driving our GraphQL API. And instead of users and businesses and so on, we want this to reflect the data that we have in Neo4j. So I'm going to stop our GraphQL API since we're going to make some changes here. One thing that's nice about the Neo4j GraphQL integration is that we have the ability to infer these type definitions from an existing Neo4j database. Let's check out the docs on this. So grandstack.io /docs, and I want how to use infer schema. It sounds like what we want. So if we already have an existing Neo4j database, this infer schema function can be used to generate the equivalent GraphQL type definitions that describe the property graph model that exists in that database. So for example, if we have data about movies and actors and users that have rated those movies, this may look familiar. This is the data model for the recommendations Neo4j sandbox. But if we run infer schema on that database, it automatically generates for us the GraphQL type definitions that we see here, which is really nice because then we don't sort of have to write these by hand. We can keep these in sync. Cool. So a nice thing about the GRANDstack starter project is that it comes with an npm script. So if we look in the root package JSON, there's an npm script for infer schema :write, and that just runs the scripts infer schema. Let's take a look at what that is. So this infer schema script is just going to run the GRANDstack CLI tool and pass some flags in there. So we're saying infer schema, then it's reading from my .env file the environment variables that are being set for the connection to Neo4j, and then it's saying write to this schema file API source schema.graphql. Okay, so what's going on there? So if you remember in the last video, when we were talking about the GRANDstack CLI tool, we said that it was something that got installed as part of the GRANDstack starter, and we said it had some sort of more advanced functionality that we might use later. And inferring a schema is one of those things. And this npm script just sort of gives us a nice wrapper on top of that. So we should be able to do npm run infer schema :write. And because we've updated our .env file, it should now be able to connect to our local Neo4j database running in Neo4j desktop, generate the inferred GraphQL type definitions based on the data that we have, and then update our schema.graphql file, which looks like it did. Cool. So this is the data that we have. So we have a single node that has the label property. Every node has an underscore ID. The underscore ID and the ID field are a bit different. So the Neo4j GraphQL library adds this underscore ID field to every type in GraphQL, and this maps to the internal node ID in Neo4j, which you typically don't want to use in most cases. That's sort of an internal implementation detail. However, it can be useful in some cases, but don't confuse that underscore ID with properties that we've set explicitly, such as the ID field. Cool. Okay, so we can see also what's interesting is that we have some fields that exist on every instance, on every one of those property nodes, and those are identified with a bang. So this is the continuous field, which I'm assuming this is, I don't know, maybe like continuous square footage or something. We'll have to dig in to see what this data actually means. And it's of type float bang, which means this is a non-nullable float, a required field. So every one of those nodes contained a value for this property, but then some things like certificate, city, state, Z, these are optional. And because our infer schema process added these as optional, well, that means that there are some nodes in the database that don't have values for that. So we'll have to think about in our application how to deal with cases where we may not know a value for that property, we may not have a value for that property in the data. So we'll have to think for how to account for that in our application. But okay, so let's fire up npm run start, fire up our GraphQL API. This will also start the React web server. I'm going to close that though, just because we aren't quite ready to work with our React app yet, since it's still set up for working with a somewhat different data model. But okay, now we can see in GraphQL Playground what sort of GraphQL API was generated based just on our type definitions. And so we can see that we have one query entry point for property, and then we have mutations if we want to create, update, merge, or delete some of these. So starting off here, let's make this a bit bigger. There we go. Cool. So property, let's look at the, I don't know, first 100 or so. And let's close the docs here. Let's return ID. We know everyone has an ID. And then address. We have a few different address properties. So this should return, yep, cool. So you can see some properties don't have an address. Actually, quite a few don't, but everyone has an ID. Let's take a look at what else do we have? We have things like assessment. We also have things like total value. Okay, so we can see that we're querying some data from our Neo4j database. If we jump back, we can take a look at the generated Cypher queries. So what's going on here is when we run this GraphQL query, so it says find the first 100 nodes with the label property and then return some of these values. these fields is called the selection set. So ID, address, assessment, and total value. That GraphQL query is then translated into this Cypher query that actually runs against Neo4j and returns our data. Okay, so that's pretty cool. Let's maybe do something a bit more interesting. Let's order this by maybe total value descending. So what is this? This is going to tell us the most expensive property in that county. So that is 915 Highland Boulevard, and the assessed value is, what, $112 million, I guess is what that means. Okay, cool. So now we can start to see how we can use some of our features that we get in GraphQL to map to some of the business requirements of our application. I should say specifically some of the features we get with the Neo4j GraphQL integration, right? This sort of query generation, this automatic ordering. We can also do filtering, which is neat. So do we have anything on square footage? Let's see. We have total acres, 34. So maybe we want to, let's say, filter now where total acres has to be, I don't know, maybe at least 10. So one thing that's nice about the Neo4j GraphQL integration is that from just our type definitions that we defined here, is the generated API includes these ordering and filtering arguments. So now we're filtering for parcels that have at least 10 acres, ordering by their total assessed value. Cool. So we can start to see how we get a lot for free with the Neo4j GraphQL integration. That's super helpful. That's going to be really nice for us when we start to look at how we can search for properties in the front end. I have a few more minutes before I have to leave and jump on another call, but let's take a look at one more cool thing we can do here. So if we have the Zillow open somewhere, here we go. So one thing that we wanted to add to our application is sort of an estimated home value feature. Zillow calls it the Zestimate. So for any house, it's sort of an estimate of how much this house is worth. And there's the Zestimate one is quite complex. I'm sure there's a lot that goes into it. We will have to look at sort of a more complex way to go about this. So for example, Zillow has this idea of comparables showing us similar homes and what they've sold for. But one thing we can do that is maybe a initial way to look at this, this estimated sales value, is, well, we have this total value. This is sort of the tax assessed value. And if we had information about the sort of percentage difference that houses in a certain market were selling over the total value, I know in the US anyway, and in most cities, in most counties, there's sort of an assessed value, which may be something like $100,000, but on average, homes in that county sell for maybe like 20% above the assessed value. So if we have some simple model like that, we can then add a computed field to our GraphQL schema that's going to be defined with a cipher query in this case to determine what is the estimated sales price based on just multiplying that total value, that assessed value, by some amount. So let's add that really quick. We'll just call this estimated sales price maybe. And it's going to be an integer, and we're going to use the cipher schema directive. So what is the cipher schema directive? If we jump back to our documentation, look at schema directives. So a schema directive is a way to annotate a field or a type definition in your GraphQL type definitions that indicates that there should be some custom logic going on. And there's a few that we use in the Neo4j GraphQL integration. Cipher specifically allows us to define custom logic using Cipher. So it allows us to define computed fields. In this case, we're defining a computed scalar field. So we're automatically injected a this object. So this is going to be a node. So if we just made this node dot total value times 1.2, so maybe our model says that houses in our market are selling for, on average, 20% above the assessed tax value. Multiply our assessed value by 1.2, and we have the estimated sales price. Cool. So let's see if we can pick that up now. We have the estimated sales price. Let's add that. Int cannot represent non-integer value. Oh, right, because we're multiplying by a fraction here. That is a float. Oops, let's cast this to an integer. So we'll say return to integer of this dot total value times 1.2. Cool, let's try that again. I think our server was starting. There we go. Cool, so now we have a total value. So again, we're ordering by total value descending. So these are the most expensive properties. So this is total value of 112 million. Estimated sales price is 20% higher, 134 million, and so on. Cool, so I think that is pretty good progress for today. So just to recap things that we touched on, we did a little bit of talking through our data model and verifying that our requirements can, at least the ones we've identified so far, can be met using the data model that we defined last time. We imported some data into Neo4j based on the data that we downloaded for a specific county. We converted that from a shapefile that we downloaded into GeoJSON, and then we used APOC load.json to import that data into Neo4j. Then in our GraphQL API, we used the infer schema functionality to generate GraphQL type definitions from that data in Neo4j, which gave us the ability to query that using GraphQL, including doing some of these filtering and ordering that will be very useful for us for our property search functionality. And then we used the Cipher schema directive functionality to define a computed field in our GraphQL schema using Cypher, specifically to calculate estimated sales price for our properties. Cool, so that I think is pretty good. We'll go ahead and stop there. I'll be sure to push all of this up to GitHub. The link is in the chat, but it's this Willow GRANDstack repo, which again I had just created last time just from the GRANDstack starter. Cool. So next time I think we'll continue on our data import journey. Next time working with some of the geospatial data that we had. We had latitude and longitude for the properties. We had the bounds, right? The polygons to work with. So we'll see how we can include that in Neo4j, and then how we can work with that geospatial data in our GraphQL API. So we'll pick up with that next week. So just a reminder, every Thursday at 2 p.m. Pacific, we'll be working on building out this application using GRANDstack. Cool. So hope you enjoyed that. In the meantime, feel free to reach out and ping me on Twitter or on the Neo4j users Slack, which you can join at neo4j.com/Slack. Cool. Thanks a lot, and we'll see you next time.